All right, ladies and gentlemen, class recording has started. So, we just reviewed the gist of fission, right? That we start off with something big, we run a neutron into that nucleus, it splits into two smaller nuclei. Lots of energy and a couple of stray neutrons. Okay, great. Reminder, right? You can't do this with any old radioactive nucleus. Doesn't work with just any random nucleus. It only works with a certain number of isotopes. And right now we've only found two where this happens. Uranium-235, plutonium-239. Those are the only two radioactive nuclei that this happens towards. If we run a neutron into any other nucleus, it just sort of decays like other things do, alpha particles, beta particles, things like that. It doesn't split and release all of this energy at the same time. Right? It doesn't slowly over time, okay? Which is great. And like I said, yesterday we went through the whole E equals mc squared thing and how the difference in mass between our reactants and the products is made up in the amount of energy that is released, right? That if we look at the difference in mass between here and here, the difference is made up by the amount of energy that comes out. But yesterday we had a discussion about the huge numbers that are involved. But if we look at it on a one atom basis, one atom is so small that the difference in mass between reactants and products for one atom doesn't amount to much energy at all. But something that scientists realize as far as this fission reaction occurs is that these two or three, depending on how it works, because it doesn't always work the same way every time, these two or three neutrons that come out of that reaction actually end up being important. Okay, so scientists start realizing that if we do this on a one atom basis, the amount of energy that's released really isn't all that great. But these two or three neutrons become important because this whole process starts with one neutron running into this nucleus, right? So, what if we could use these two or three neutrons that come out of there and run them into another uranium-235? Now, instead of just one atom splitting, we would have two. And the amount of energy that's released increases. But out of those two that are split, right, you get four new neutrons. And if you run those four neutrons into four new uranium-235s, right, now we're getting somewhere. Okay? So that process where we're using the neutrons that are released from the original fission reaction to start new fission reactions in other atoms, we refer to as a chain reaction, right? The neutrons released during fission can be used to split other unstable atoms. The fission process starts with a neutron running into uranium-235. When that happens, you get two new neutrons that come out of that, right? If we line up everything right, those neutrons run into another set of uranium-235s, and the process starts over. If we don't do anything to check that process, right, or to slow it down, it just happens boom, 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 and all that energy from all those atoms gets released at once. When that happens, that's what we call a nuclear bomb, right? Or some other kind of nuclear explosion. But first, are we okay with the picture that's on the outline? Do I need to show it, or is it pretty self-explanatory? Pretty self-explanatory. Okay. So yeah, I mean the neutrons that come out, they run into new ones, right? So that gets us into if we can release the energy from several of those atoms. And now when I say several, I'm not talking about like 20, right? But like we talked about earlier in the year, even if you have 1 gram of uranium-235, you're talking about, 10 to the 20th power number of atoms, right? It's a lot of energy that gets released. Okay? Actually, I had my physics classes calculate this in their previous test, and the amount of energy that was released in nuclear bomb explosion amounts to less than 1 gram of uranium. So less than 1 gram of uranium that we turn into energy is enough energy to destroy, an entire city, right? Maybe, yeah, it's a good phase. Wish we could get that on recording, So I would put a little cover over your eyes so nobody would know it was you, but so. But just as a side note, just for fun, because people were asking in physics when we did this calculation, they said, okay, well, what about me, right? You're all mass, okay? So we basically looked at, and we did the calculation, if you had a 200-pound person, okay? Because the person who asked actually was a bigger guy. So if you have a 200-pound person, if you could take all of that mass and turn it into energy, how much energy would that be? And we did the calculation, and it comes out close to, if we could take a 200-pound person and turn that person completely into energy, it's the equivalent of close to 100,000 nuclear bombs. Like, that's how much energy is wrapped up in mass. It's a very, very concentrated form. And if you can release that energy, right, you guys have seen the videos and the pictures before, right? And if you haven't, you probably will in social studies sometime over the next couple of weeks, because I hate to be a spoiler for you, but that's how the World War II unit ends, all right? So that's, but, like I said, in a social context, right? And don't go quoting this to your history teacher, because I don't know if this is actually factually accurate, but so as far as our involvement in developing the nuclear bomb, right? This is all happening, these discoveries of fission and what we can do with it are taking place in the late 1930s, early 1940s, right? And the first chain reaction actually happens at the University of Chicago. The first chain reaction wasn't a nuclear bomb, all right, so don't right? But this idea that one atom and the neutrons released from fission then start the fission on another atom and another atom and another atom, and releasing energy, bigger amounts of energy than just one atom, where it actually happens at the University of Chicago. They actually did it in one of the gyms there. They set it up, and I think they put blockade stuff around it. I don't know for sure, but but they set it up in one of the gyms, and they just, here you go, nuclear reaction, yay, here it is, right? But so they start doing this work, but the scientists here in America know that if they're figuring these things out, then scientists in Europe, especially in Germany, are also figuring these things out as well. And the scientists here in America come to a decision that if we don't develop this weapon, the Germans are going to develop it. And that's bad for us, right? So that's great, and scientists saying that we should do something is good, but politicians don't always listen to scientists, right? I'll reserve editorial comments for later on, right? But politicians don't always listen to scientists, except for one scientist. All right? Buddy? Einstein. If Einstein says something, you probably should listen, right? So, the other scientists who are Einstein's really not working on fission. This isn't really his thing. But he obviously understands the science behind it and what's going on. And so the other scientists who this is their thing, they go to Einstein and say, we can tell the government all we want to, but if you tell the government, it's It's going to mean something. And so they convince Einstein to write a letter to FDR, Franklin Delano Roosevelt, president at the time, and basically says, hey, we got to do this. We got to make this bomb. Because if we don't, they will. And that's going to be bad, right? So that letter convinces Roosevelt that, okay, I guess we got to do this. And then that gets us into the Manhattan Project. Are we familiar with the Manhattan Project? At least by name, right? Yes, no, maybe? Yeah, okay. So Manhattan Project is the process of us developing the nuclear bomb, going through the steps of getting the materials that we need, especially the uranium-235, okay? And then putting that uranium-235 into a working weapon, right? Uranium-235 is not a common isotope. If you look, anybody got their periodic table out? Sorry. Why would we have important information ready? Okay, so Mark, uranium is atomic number 92. You see it down at the bottom?
Yep.
Okay. What is the average atomic mass of uranium?
238.03.
238.03. Meaning that most of the uranium that exists out there in nature has a mass number of what? About 238, because the average is very close to 238. Uranium-238, most of the stuff that we get out of the ground doesn't do fission. Only one isotope of uranium, uranium-235, is the one that does fission. And percentage-wise, it is a very small amount of uranium, or a very small percentage of the uranium that we get out of the ground. So we have to go through the process of separating that uranium from all the other stuff that's not what we need. Have you ever heard of the idea of enriching uranium before, or developing weapons-grade uranium? That's what it involves, okay? This is the kind of thing that when rogue states or countries that we consider to be bad, right? Not naming any names, but we're looking at you, Iran, right now, okay? So right now, our government is, and many other governments around the world, are convinced that Iran is trying to develop a nuclear weapon. If you look at what they're doing in their country and the facilities they're building and stuff like that, our conclusion is they're trying to build a nuclear weapon. But even if you have the facilities, if you don't have the uranium to do it, it doesn't really matter. So that's really sort of the problem. That was part of the Manhattan Project as well, is we have to figure out how to get this uranium, and only the uranium-235. That was part of it, and then we took that uranium, took it out into the desert in New Mexico, and we made a bomb out of it, and the rest is history. So, literally. So, Eric's good.
Wasn't Einstein German?
Yes. Actually, Einstein was Austrian.
So why would he help America then?
Because he was also a Jew. So he realized what was going on in Europe and got out of there. Because if he didn't, again, the rest is history, right? So yeah, I'm not 100% sure, but I think he became a naturalized American citizen when he moved here. Not 100% sure on that, but yeah, he was. Yes, he was. I think Einstein was Austrian, actually, I believe, if I remember right. But he was also a Jew. And so not a lot of scientists, but there were several German and Austrian scientists who were Jewish who left Germany because they were scared of what might happen to them, and actually came to work in America and eventually worked on the Manhattan Project and helped us develop the atomic bomb. Now, that being said, we never actually had to drop a bomb on Germany, right? That's not where we use those atomic bombs, right? But that would have been an option if we hadn't eventually, figured out a way to defeat them without having to drop a bomb on them, right? Which goes into the process of the decision making about to use the bomb. That if you read estimates of generals, especially MacArthur, with MacArthur, you'll learn about him. MacArthur was in charge of the Allied forces in the Pacific, and places like, if you hear about like the Battle of Iwo Jima and Midway and those little Pacific islands, MacArthur was all kind of like involved in that. But his estimation was that if we were going to invade Japan and try and end the war that way, probably upwards of 1 million people would end up dying. Our forces, their people, their armed forces, and stuff like that. That was, I guess, sort of like the estimation. Is that if we're going to invade Japan and end this war, 1 million people would end up dying. Now, so we drop a bomb on Japan and only like 150,000 people died. But apples and oranges, I guess. I don't know. So basically, we said, hey, after we developed this bomb, we said, okay, listen here, Japan, right? We got this bomb, and it's going to destroy a city. We're going to use it on you if you don't surrender. And they basically said, whatever, right? And so we dropped a bomb on them, right? And then, so we said, okay, if you don't surrender now, we're going to drop another bomb. And they said, whatever, we're not going to surrender. So we dropped another bomb and basically said, okay, are you happy now? Are you done? And they said, okay, fine, okay. Which was good because we didn't have any more bombs. So we only made 2, and we used them, so it's good that they surrendered at that point, because after that we would have been like, all right. So you called our bluff, but that didn't happen. So, all right, are we good? Social context, right? That's one of the reasons why I like doing this section, because there is a lot of, and so you can kind of, if that comes up in history, we can talk about it a little bit. Hopefully you'll talk about these things in a little bit more detail in history, because that's, my science teacher impression of what happened. So. But anyway, after development of the atomic bomb, a lot of scientists feel bad about it because they realized what they had done. And so Einstein actually goes on a crusade and basically kind of becomes like a world peace guy. He's like, okay, we can't do this again because look what happened the last time we did it. And so he becomes like this advocate of peace and understanding and stuff like that. But scientists realize that the energy that's released in this fission process, it doesn't have to necessarily go to destroying cities. There's other ways that we can use it. And so today, we actually use it quite frequently in a nuclear power plant. A nuclear reactor uses a controlled chain reaction to release a lot of energy, but we control the amount of energy that is released. At least in most cases we do. All right. Here is a picture of how a nuclear power plant works. I have some change for you here. There you go, Keith. All right. Here's how a nuclear power plant works. First, going back to our electricity and magnetism unit, do we remember how a generator works? Basically. All right, Marco.
Basically, it creates, you make energy and you turn a turbine, basically.
Right, so it's a coil of wire, right? Because we said that as a coil of wire spins in a magnetic field, it creates current, okay? Over here, the electric generator has a big coil of wire and a couple of big magnets, and it spins them around. And as it spins them around, it creates current, and that's the current that ends up going into our houses, okay? Now, The important part is it has to spin. So something has to make it spin, right? If you go to Niagara Falls, what makes the generator spin? The falls, right? The water going over the falls or the water in the river leading to the falls makes the generator spin. Great. If you go to the Science Center, anybody ever been to the Science Center before, right? What makes the generator at the Science Center spin?
Wind turbine.
The big windmill that's out there, right? So as long as it spins, we don't care how it spins, but it's got to spin, okay? At a conventional power plant, here's what we do. We heat up water, and we turn that water into steam. And that steam travels through a pipe, and we shoot it on the generator, and it spins the generator. That's pretty much how it works, okay? In a conventional power plant, like the one in Avon Lake and a couple other places that are around here, right? If you drive down Lake Road west, you go past the power plant, they use coal to heat up the water. But it doesn't have to be coal. As long as you heat up the water, you heat up the water. So in a nuclear power plant or a nuclear reactor, instead of using coal to heat up the water and turn it into steam, they use a nuclear fission reaction. A nuclear fission reaction releases a lot of energy. That energy goes into the water. So here, these uranium fuel rods, these are the purple ones down here, okay? Fission happens down here, and it releases a bunch of energy. And see this red part? All this is water. And it heats up the water. And they pump this water through a pipe. It's closed because you're using radioactive materials to heat it up. And it heats up another tank of water. This tank of water turns into steam. They run it through a pipe. They spin the generator. Current is created, and it goes to your house and runs your computer or whatever. And then that water, they collect that water, that steam, and they run it back through into that tank again. The water that got heated up by the nuclear fission reaction goes through, gets cooled down, and then they pump it back into the same tank, and they heat it up again, and they run it back through. And this is how a nuclear generator works. The only thing we're using the energy from fission to do is to do what? Heat water. You're boiling water with nuclear fission. That's all you're doing. All right? Whether you do it with coal or whether you do it with nuclear fission, it's still heating up water. Okay? Good there? Nick, go ahead.
How come the water in the tank of the uranium don't turn bigger?
Because it is closed. Okay? So remember that we talked about that phase changes are not just temperature related, they're also pressure related, right? The pressure in this tank is immensely high. But remember that we said that pressure relates to how close the molecules are together. Does that sound familiar? Right? So the pressure in this tank is huge. But that keeps the water from turning into steam. And it also allows the water to get above 212 Fahrenheit or 100 degrees Celsius because the pressure is so high. Remember, it's not just a temperature thing, it's a pressure thing. So it's really, really hot water that is enough to boil this other tank. Now, that's the problem, though, when we have a nuclear accident, okay? If something goes wrong with this system, if the water gets too hot, the pressure starts increasing and that water starts turning into a gas. What do we know about the volume of a gas versus the volume of a liquid?
Much bigger.
Much bigger, right? So what starts happening to this closed system that has all this water in it? Right? It's like a balloon popping, okay? Which in itself really isn't the problem. The problem comes because if there's no water in this tank, because it turns into steam, all this energy that's being released from the nuclear fission Doesn't have anywhere to go. So it just goes out, right? That's a nuclear accident or a reactor accident. Sometimes we refer to that as what? A nuclear meltdown. In a nuclear meltdown, here's what happens. This whole system, you can see here, concrete. This whole system is basically encased in a huge concrete building. But as strong as concrete is, if you get it hot enough, what happens? If you get a solid hot enough, what happens to it?
Starts to melt.
It starts to melt. Concrete is no different. The energy that is released from these uranium fuel rods, because it doesn't have anywhere to go, right? It doesn't have any water to heat up, right? It just starts heating things around it. So the floor of this, guess what happens to it? It melts. And then when it melts, what happens to these uranium fuel rods? And then they run into this concrete floor, and guess what happens then? It melts, and then guess what happens to those uranium fuel rods? And now they're in the ground. And that's a problem with all of our drinking water and, you know, animals and grass that we let the animals eat and all that stuff, right? So that's a nuclear meltdown, right?
Does this all take place in those huge cooling towers?
Yeah, pretty much. Those cooling towers, that it's not open to the air like that. I'm assuming you're talking about like those kind of like
Yeah.
cone-shaped. They're not cone-shaped really. I guess I don't really know what they're like.
I don't know.
They look like
They're
this,
huge cooling
right? They
towers,
look
so-
like
Yeah.
they look like this, you know, right? So that's more of an exhaust. That's more of an exhaust pipe. That's more the exhaust for this, if I'm not mistaken. Why they're that like characteristically shaped, I don't know. So I'm not sure if that's like a design characteristic or if it's just something they thought was cool or whatever, right? But yeah, I'm pretty sure that's the exhaust more for here, because this steam, it's just steam, right? Just like a regular power plant gives off steam too. It has to, right? That's not the dangerous steam. This is the dangerous steam over here. So now, my gosh, it's been 4 years, I think, since the big tsunami hit Japan. I think it was 4 years ago, maybe 5 years ago. Are you familiar with the big tsunami that hit Japan? So one of the things that happened was they had nuclear power issues, right? A nuclear power plant melted down. The problem that they were having there was that this water, this red water that gets really, really hot in the nuclear reactor, right? It has to move. It has to, like, because we take the hot water away and replace it with cooler water and heat that water up and then take that hot water away and bring it up. The problem that they had was that the tsunami knocked out the electricity part of the plant. And if there's no electricity, the pumps that move this water don't work. And if the pumps don't work, this water that's in here, Nick, that's when we run into problems with this red water. It gets too hot. And now it will eventually turn into a gas, even though it is in pressurized container. And that's what was happening, is that they couldn't keep the water moving, and they would pump water in like from the ocean to try and cool it down. But if the water doesn't move, it just gets really, really hot and it boils away, and you got to put more water in, right? So that was the problem, is that the electricity was out, and they couldn't move this water around, and that's why we run into those kind of situations. Right? Good there? Yeah. Any other questions? So, just to fill in your outline, right? Here, a fission reaction occurs, and the energy that is released turns water into steam. Not directly, it's kind of like a two-step process. The energy heats up this water, and then this water turns the other water into steam, but eventually that's what it does. And then that steam, right, that's where the water is turning into steam, okay? And then that steam eventually turns a generator, right? Turns a coil of wire in a magnetic field, and when you turn a coil of wire in a magnetic field, you create a current. And that's what a nuclear power plant does. The operation is very similar to the operation of a conventional power plant. It's just that the only thing that's really different is how we heat the water up. In a conventional power plant, we use coal. In a nuclear power plant, we use nuclear fission. Good there. All right. By the way, Ohio, 2 nuclear power plants. Okay. There's one, if you've ever taken like the back roads way to get to Toledo, if you take Route 2, up through or up through in that general direction towards the northwest, towards Toledo, you can drive right by it. You can see it from the road and that's the Davis-Besse nuclear power plant. And then there's also one on the east side, past Mentor, if you go past that way, in Perry. It's the Perry nuclear power plant. So 2 nuclear power plants in Ohio. I don't know when the last time both of them were running because they're starting to get old and they have to shut them down and make repairs to them and stuff like that. But we do have 2 nuclear power plants in Ohio. So. All right, good there. Okay. Let's go the other way. Fission takes something big and breaks it down into smaller things. But fission, if we talk about it in terms of using it for electricity production, fission is not a renewable resource. Eventually, we run out of that uranium-235. And when we do, we can't do fission anymore. And when we can't do fission anymore, we can't run power plants that way. Although most people don't want to run power plants that way anymore anyway. All right? But fusion is a better option. Well, I shouldn't say better. It's not a testable question, right? Fusion is another option. Whereas fission takes something big and breaks it apart, fusion takes something small and makes it big. Right? When we fuse something together, we take it and we put small things and we put them together. Right? So in a fusion reaction, we're taking 2 smaller nuclei, combining them together to form a nucleus with a greater atomic number. During that process, a small amount of mass is converted into energy. And we've already gone over that if a small amount of mass is converted into energy, even a small amount of mass converted into energy releases a lot of energy because of the whole E equals mc squared thing. But the conditions required for fusion don't exist naturally here on Earth. So let's look at a picture. All right, ready for the picture? Don't be blown away by the quality of this picture, because it is like, whoa, right? And that's like Picasso quality right there. So anyway, we take 2 isotopes of hydrogen. One is deuterium. This is hydrogen 2, 1 proton, 1 neutron. And this is tritium, 1 proton, 2 neutrons. Okay? What we're doing basically is we're taking these 2 and fusing them together into 1 nucleus. Seems simple enough, but we run into some pretty serious problems in trying to do this. What's a serious problem that we run into in trying to fuse 2 hydrogen or nuclei together? Repulsion, right? Repulsion. These 2 nuclei, they don't want to be next to each other. It's not the neutron's problem, right? It's the proton's problem. This proton and this proton do not want to be next to each other. They will not come together on their own because they repel each other. They will only come together if forced to do so, right? That requires a lot of energy. If we get these 2 nuclei moving very fast, all right? As we heat things up, what happens to those particles?
They move faster.
They move faster. If we heat them up fast enough, they move so fast that when they run into each other, they don't have a choice. They stick together, right? They can say they don't like each other as much as they want to, but if they're moving fast enough, They're going to run into each other. And that's and that's what happens here. So, both of these small nuclei are positively charged, and that means that they repel each other. All right? Because all protons have a positive charge, and that means all nuclei have a positive charge as well. The only way to get them to stay close together is to raise the temperature really high and make them move really fast. Are we figuring out the outline? Not sure why that one line over there is heat, or on the way over the far end is. So letter C number 1, right? All protons have a what? Positive charge, right? And in order for the small nuclei containing protons to form together, they must have a lot of energy. You could go heat if you want to, right? I'd probably go energy. And then for number 3, right, this high amount of energy is only obtained how? High temperatures. Nick, building on something that we talked about before, another way we could do it is what? Yeah.
Increase the pressure.
Increase the pressure, right? We said that those two things could work together, right? That we could increase the pressure. But those conditions, the amount of temperature that was required to make these two nuclei stick together, doesn't exist here on Earth. We can artificially make it happen, but it doesn't exist naturally here on Earth. Generally, to finish this up, right? During that process, when they combine, small amount of mass is turned into energy. Illustrated by these awesome lightning bolts that are coming off of that. If we want to be technical about it, right? Those lightning bolts would be in the form of what? Those lightning bolts are representing.
Electromagnetic waves.
Yes, which we called earlier in this section.
Gamma rays.
Gamma radiation, right? That's gamma radiation. Just like it comes off during a natural radioactive material, same thing. That's gamma radiation. So, if we can't do it here on Earth, right? So we got two options. Either we make it happen, or we get it from somewhere else. Where else does this happen? Stars, right? That's where it happens most often, right? So, in a way, when we talk about using solar power, right, we're using fusion for our energy needs. If you look at the amount of energy that is released during fusion versus the amount of energy that is released during fission, fusion actually releases more energy based on the amount of materials that you start with than fission does. But right now, the amount of energy that we have to put into it to get those things to a high enough temperature and a high enough pressure to make them stick together doesn't balance out the amount of energy that comes out of it. We can make it happen, but the amount of coal and other sources that we would have to put energy into them to get them hot enough doesn't make it worth it. And that's why we don't use fusion right now as a energy source. Andy, go ahead.
Are those isotopes of hydrogen common?
They are more common than uranium-235, but not like real common, right? If you look at the average atomic mass of hydrogen, it's like 1.01. So yeah, those aren't very common. Although this one here, anybody ever see Spider-Man 2? Not the amazing Spider-Man 2, Spider-Man 2, right, with Doc Ock. Yes, right. Throughout the movie, Doc Ock is trying to get himself what? Anybody remember? Yeah, you know what that? He was trying to make the little ball thing, and he had to get tritium to do it. There it was. Doc Ock is basically trying to make himself a little fusion reactor, and he actually does at the end of the movie. So, yeah, but it's Spider-Man. What? With his little robot arms, you know.
Yeah, I'm so.
So,
Like walks on
Yeah,
them?
but don't be confused. That's not the Amazing Spider-Man 2 that's coming out in a couple weeks or whatever. So, what? I never saw the Amazing Spider-Man because I really couldn't quite understand why we had to remake Spider-Man after remaking Spider-Man like 10 years ago. Like, why did we have to make Spider-Man again?
They made a comic, they made a movie. and then they
Yes,
made
because
another
people will go
movie.
see. Even Eris, who thought it was terrible, but he still went to see it. I mean, it's, anyway, all right. The reason why we end this section on diffusion is because this is how most of the energy in our universe is released, through this process that occurs in stars. So we will transition this into, okay, now that we get this started, how does it make a star? And that's where we're headed next, right? We said that this section starts with the very, very small, things like nuclei of atoms, and ends with things that are very, very big, like stars themselves. Okay. Good there. All right. Let's wait for it, everybody. Oh, there it is. Look. Woo. Good job, everybody. It only took us like 3 days. So, not your fault, but just kind of a long thing. So, do you have a question or go?
Yeah.
Go ahead.
How does mass get changed